Okay, 5 in the afternoon in Brisbane, Queensland, Australia. Welcome to Math7501. I'm Yoni Nazarathi. We also have Tim Butsworth here. He'll introduce himself shortly. We're the course lecturers. Tim will be doing the majority of the lecturing. Somebody put in the chat, this is a Yoni day. Yes, I've had the pleasure of having you guys both for Data 7001 and Math 7501. So a good part of the cohort has seen me earlier today. What time is it in China? For those of you in China, just get a feel for it. It's 3 in the afternoon. And in India, hour and a half before that, is it 1:30 in India? 12:30. Oh, okay. The day is young in India. Okay, great. So here in Brisbane, we'll be pushing till 8 in the evening. And that's so we have a kind of significant amount of time to work on the course. So welcome to the course. I'll overview a few things from the course website and introduce myself, and Tim will introduce Tim, and then Tim will introduce himself as well, and then we'll get right to it. So you've probably seen this website. We've heard quite a lot of your voice recordings, so thanks for those of you that sent your voice recording to the mailing address. If you haven't, please do. You'll need to submit such a recording anyway with assessment, so it's kind of good practice to put yourself on voice and put a recording, but I found it very interesting to listen to your recording. So if you did not get a response from me, then I still haven't heard your recording, and if you got a response, then I clearly did. Okay, so this is one of 4 bridging courses in the Masters of Data Science, really, right? So we've got Math 7501 and next semester Math 7502. There's also a programming course, and there's a data basis course. These are kind of the bridging courses. Now, the first question that many of you are asking yourselves is, hey, do I need to be in this course, yes or no? And often during the years when I've met students, often live in class, the answer was no. So a way for you to assess this is, first of all, yeah, you can take part in today's lecture and future lectures, etc. But a way for you to assess this is to look at the course reader, which I'm sure many of you have looked at already, and to see how many of these things here are foreign to you and how many are things that you have studied, have worked with before, etc. For example, if you are a civil engineer by training, or a mechanical engineer, or an electrical engineer, you've done a whole lot of calculus and have worked with matrices as well, but maybe you haven't done units 2, 3, and 4, which deal with discrete math. And then you will ask yourself, hey, do I need to do the course just for units 2, 3, and 4? And the answer is probably no. These are things that you can make up yourself and just pull this course reader later on in your Masters of Data Science program if you need. However, there are often students, and some of you are here, that have been in industry for a decade and a half, and it's great to have you back on board here with us in academia. And if you feel you want a refresher, even though you've done derivatives and integrals, even at a level beyond what we have here in the course, then that might be motivation to do this course. I've also found that a good part of you are learning in English for the first time, and actually taking part in a course where you are learning things that you might have done quite a lot in your native language, often in Mandarin, but also in other languages, and you suddenly see them in English, so that can be useful. So go ahead and make that decision. Happy to help you with that decision. So drop me a line or meet me in my consultation hour. Happy to have you here, but also understand if you prefer to choose a different course. For example, if you feel you know a lot of this, one thing you can do instead is a course of financial mathematics a semester or something else. Okay. Go ahead and interject with questions at any time. Data 7001 lecture today was very dynamic, so that's good. Let me just pull up my chat. I see it. Okay. Now, our purpose in this course is to get you to read, understand, and do some computations and some logical reasoning in the language of mathematics. Okay, it's slightly different than a first-year calculus course in an engineering degree, where at the end of the course, you should be extremely proficient in doing integration by parts and integration by substitution and partial fractions and know all the tricks and shticks. You'll still need to know some of these tricks and shticks, but it's more about speaking the language. Due to that, we actually chose Mathematica, and we've had that since the start of the course, as the programming language or the software package that we use. So as a data scientist, Mathematica might not be the first thing that you use. And one of the reasons, by the way, is simply because it's licensed. So you don't have a free license. If you'll be working in a startup or maybe even in a big company, getting a license for Mathematica can be hard. But the reason we're using Mathematica is because Mathematica is kind of symbolically, it's naturally symbolic. It's a language that allows you to do a lot of those mechanical computations, which we'll do, certainly integrals and derivatives, but also evaluation of series and other things like that symbolically, and we'll see that today. Some people use Mathematica later on for machine learning and data science, so it's another thing that you'll get from the course as well. Okay, so that's for the software. Our tutor running the practicals and in charge of the assessment is Dr. Amina Shausan. She's an expert in probability, has a PhD from University of Queensland. She's also in tutor in data 7001 this semester. Okay. Now, there are all these points of contact here. So Blackboard, obviously, you know, in the course profile, you probably know. There's a GitHub repo for the course. So in this GitHub repo, there's nothing at the moment, but for example, today we'll do some scratching on a notepad, upload that to GitHub, do a Mathematica notebook, upload that to GitHub as well. There's a Piazza page for the course, which I'm sure you know. Go ahead and use Piazza freely. Please don't expect an answer from the teaching staff immediately, but rather with a delay of around 48 hours. The best thing is that you actually try to answer your peers' questions. And when we see that the question is unanswered, we'll interject. Okay. Feel free to send me an email about anything, the lecture email, and during the weeks that Tim will be teaching, then to send him emails about anything as well, but continuously to me. I'm the course coordinator throughout. However, we will not, well, we'll just tell you kindly, please don't send technical questions by email. Okay, so technical, I mean, you know, how do I solve this? How do I do this? How do I compute this? Why is this like that? We have Piazza for that. Email should be used for administrative issues, etc. Having said that, almost every semester I make some silly typo in the assignments, and then there is some great student that sends me an email about the typo, and we really appreciate that. Hopefully there won't be one this semester. So that's these things. For those of you that really feel that mathematics is, I need to do mathematics, or you haven't done it for a while, or just want to feel a bit more comfortable, or even if you are feeling comfortable and just want a bit more help, feel free to head to the Mathematics First Year Learning Center. And when I say head, of course, I mean virtually head. Okay, so the First Year Mathematics Learning Center, there's some excellent tutors there that can help you further. They might not know the course directly, but there's all these courses at the University of Queensland which are for undergrad students, and this course is a combination of these courses. Okay. We've got a detailed week-by-week schedule of what's happening. So today you have me and Tim. Okay, but Tim will just say hello, and then we'll be free to peel off or stay as he wishes. And I'll be pretty much teaching the first 5 weeks, and then Tim will be doing the second half or the second 2/3 of the course. And in the last lecture, I'll join again and say hi. But still, you'll see me in the quiz and things like that. Okay. So that's our schedule. The schedule maps to units. There are 10 units. Okay, and these units are the same units that appear also in the course reader. Okay, if you look at previous years, there was a slight reshuffling, but this has been the units at least for one semester. I got a message that my internet connection is unstable. Can you hear me okay? Yeah, let's hope it was just a glitch. Okay. So if you click on these units, when you go, for example, to unit 1, what you'll see is some old lecture videos. And you'll see that it actually says unit 6, but that doesn't matter. That's unit 1, basic operations on matrices. And feel free to watch these videos. And you'll also see some videos collected from YouTube that we found to be especially useful for this content. Now, that's a lot to watch, and you might not want to watch it all, but when you feel you want to see a bit more on something, feel free to click on the unit and then see some additional videos about that specific thing. Okay, so the fact is that YouTube has some excellent content, and we've curated this content here to kind of fit the course, but the YouTube stuff is really kind of an addendum to what we'll be doing. For example, nothing in the YouTube videos that's not in the lectures is accessible. Okay, so these are the units. So basically, what we'll do today, and it'll probably take a bit more time next week, is deal with matrices and vectors. Now, you're here in matrices and vectors, and you're thinking, "Ooh, linear algebra." Well, it's not the, let's say, the mathematical, theoretical part of linear algebra dealing with subspaces and eigendecompositions and things of that sort that you're going to do in the next course, which I highly recommend, Math7502, taught in next semester. But what we'll do is more of just the formal part of how to add vectors, matrices, do a bit of matrix multiplication, deal with basic things like inverses and determinants and things of that sort, maybe see a quadratic form, etc. Okay, so it's just calculating stuff with matrices, not much more. And then we go for about 3 weeks on discrete mathematics. Okay, so this is what's taught in UQ in a course, I'll put that in chat, called Math1061. Okay. But we're teaching a subset of what's taught in Math1061. And then the rest of the course deals with well, you can call it in a fancy way real analysis, but no, it's calculus. Oh, sorry, I put that just in a chat to somebody, Math1061. Let me put it for everybody, Math1061. So then units 5 to 10 are similar to what is taught in the course Math1051 at UQ. Okay, so these are kind of undergrad courses taught to big amounts of students. However, we do go into multiple dimensions, which is often just taught in Math1052, which is kind of the second semester course, even though we might not do it very formally. So just because, so in terms of understanding the language of mathematics, you want to understand multiple dimensions. Okay, in terms of assessment, 6 items, not too complicated. So you've got assignment 1, which should be out soon because it's due soon. Okay, and I realize that this deadline also coincides with the deadline for data 7001. So you'll just have to time things so you're efficient. Assignment 2, focusing on other units, and then assignment 3. And then you've got 2 quizzes and a final exam. Okay, so we can treat these pretty much as 3 quizzes. Now, one thing you might notice is that the final exam, for example, does not assess you on units 2, 3, 4. So in that case, this is slightly easier in the sense that you are kind of learning something, being quizzed about it, and then telling it bye-bye in terms of assessment. Okay, that just has to do with the fact that many of you are going to be, this might be a bit of a difficult thing for some of you that have not done mathematics for a while or have not done a lot of mathematics. Okay, so the final exam pedagogically is treated as an extended quiz. The 2 quizzes are taken during class, and basically what happens on March 23rd, I guess is that a month from now? Yes, a month from now, we'll say, hi guys, give you a link to the quiz. You'll do the quiz, you'll write it at home, you'll take photos, you'll send it to us. Instructions will be clear. It works. And you'll do it individually without plagiarizing, etc. Okay. So that's how the quizzes are done. Final exam will be done in similar conditions, but perhaps in slightly more organized conditions. All right. Okay, how do you submit things? So all submissions go to this email address, which is where I'm still waiting to get voice recordings from a few more of you. Okay, and there are direct instructions here. And you submit with an audio clip, just like these voice recordings I'm asking to hear from you, where you can say, hi, thank you very much for the assignment. I really appreciate it. No, you can say, hi, I enjoyed the assignment, or hi, I found the assignment hard, or hi, I found these and these questions hard, but this question easy, or I found this interesting and this mundane. Okay, and I did not plagiarize. I did not copy from anybody else, except for discussion in Piazza on this and this and this question, okay? Or anything of that sort. Okay, so that's this audio clip that you put, and indeed you won't plagiarize. Are there questions about all this content? Well, all this admin content. It's late in the day here in Brisbane, but we found out that in Asia, it's earlier for many of our students in Asia. No questions so far? Okay, I'll just speak about myself for a microsecond, also because many of you have just seen me in the other course. So I've been at UQ for just about a decade. That's me. Feel free to connect to me if you want. I'm Israeli originally. I grew up in Israel and then the United States, and then back in Israel, did some military service. I worked in industry for about 5 years in software development. Then I did a PhD in applied probability. I've been in data science for the last long while. I'm called the data science lead at the School of Math and Physics. So that's our school's part of your Master of Data Science program and other things related to data science. Yeah, that's me in a nutshell. Tim, I spoke quickly because also heard more and saw more about me in the other part. But I'd also like to introduce and here Tim will introduce himself. So I've known Tim actually now for at least 6 or 7 years. I think since you were an honor student at UQ, but since then you've done many things. So go ahead, Tim.
Thanks very much, Yoni. It's good to be with all of you this evening, and I'm very much looking forward to an opportunity to working with you later in the semester. So I actually did my PhD in geometric analysis, so not data science. In geometric analysis, really what the name of the game is studying differential equations that arise in the quest to find geometries that curve in particular ways. So I noticed in the chat someone was asking about differential equations. That makes me feel good because it's a subject that's very near and dear to my heart. So yes, as I said, no formal training in data science. However, quite recently I've become quite interested in the subject as my own research has started moving closer to that sort of arena. The reason this sort of subject interests me a lot is that, well, in any subject, many fields, health, engineering, all the way to the sort of pure mathematics that I do, really what the point of your job is to draw reliable conclusions about the behavior of a certain system, whatever it is you're dealing with. Now, in order to extract useful information, you need to do it from very, very large sets of data. Of course, in order to be able to treat this data properly, most of this is usually done with a computer. But in order to be able to interpret what a computer is telling you, and in order to be able to understand whether it's telling you anything meaningful or not, and in order to have the computer work efficiently, you really need to include some mathematics in the mix there. And this is actually goes back to something that Yoni said originally, that mathematics, at least the sort of mathematics that we'll do in this course, it's a language. Really, a lot of the concepts I think that a lot of the concepts that you'll come across in this course, you may have some familiarity with them, but really what we really want to do here is formalize it with a language, because this is what allows us to communicate these ideas efficiently with each other. And this is how we can efficiently communicate ideas with a computer, for example. So that's a bit about me and my interpretation of the benefits of studying data science. I'd like to commend you all for starting the journey in studying data science, and I'll look forward to speaking with you later on in the semester. Thanks very much.
Sorry, I was muted. Thanks, that's wonderful. And you can reach Tim's website just from here. I'd recommend just looking at a paper or two of Tim, so getting a feel of what geometric analysis is. It's really far from us, but as Tim connected very nicely, There are a lot of connections that he can make during the lectures. Now, speaking about connections, what you'll see in the course reader is that for every unit, we also present an application. Okay, in terms of a bridging course, this is really a mathematics course. Okay, it's a course about the language of mathematics. It's not a data science course that we're doing now. That's, by the way, different from Math7502 next semester, that can connect much more to quite a strong suite of algorithms during dealing with linear algebra and data science. However, because, to keep you motivated and connected to data science, in each unit we'll discuss briefly about some application which has a data scientific relation, or related to data science. Okay, so for example, here in 4, we'll speak briefly about a pre-trained neural network, even though what we'll study is relations and functions, which are really kind of very dry things dealing with with the fundamentals of mathematics, with tuples. You'll see what that's about. Okay, and similarly in unit 5, when we get to the latter units, and of course things when we're speaking about functions, etc., we can connect it to statistics, or just to profit maximization, which essentially is a lot of what we're trying to do in the broad sense of things, optimization, and just a bit more probability, and finally just speaking a bit about neural networks. Okay, so this will not be a lesson of how to, but we'd rather connect the mathematics that we do to these things. Okay, and I think we can start. Let's start on unit 1, and what I'll do is I'll jump between Mathematica and the electronic pencil. Let's see how that works. I must say that today I'm using an iPad that is a bit smaller than the one that I typically use. So I hope it will work okay. So that's an iPad for writing. Let me share my my iPad screen. And let's get to it. Now, you might be asking yourself, what's the best way for you to participate now in class? Okay, so first of all, we'll try to interject with a few questions, etc. So there'll be some things you can think about. So that's clearly ways in which you can participate. But what you can do is if you can annotate yourself over this course reader in a similar manner to what I'll be doing in the next couple of weeks, then that might be a good thing to do. So I haven't printed myself since COVID broke out. For a year and a half, I haven't printed, well, a year and a bit. Okay. But if you can print, then maybe print it out and write on it. Or if you have one of these electronic things, and then write on it. Having pen and paper in general, just to do some hand computations, can be good as well. And have Mathematica open if you can. I'm looking to see then. Oh no, that's a direct message. Okay, so I'll move on. All right, so for the next while, we'll be speaking about basic operations with matrices and vectors. Okay, and warning sign, dry stuff ahead, but we'll make it interesting. Okay, so, well, let's actually just start with a matrix. So we've got here a table. This is not a matrix, this is a table. And as you'll see in your introduction to data science course, or you might have already seen it, if you've done the intro to data science before, when you think of data, the most basic way of thinking about it is in terms of variables that come here. This is a variable and a variable and a variable, etc., up to a variable, and observations. Okay, so your rows are variables, and your rows are observations, your columns are variables. Okay, that's one way of doing it. I'll answer the question in the chat in a second. Okay. Now, when when you treat data like this, you can have all kinds of things. You can have missing entries. So you can have some entries that are missing. You can have entries that some of them have a date and some are string, meaning sequence of characters, and some are numeric, etc. And that's what data science is about, dealing with data sets like that and making sense of them. Of course, data sets can be much more complicated as well. Okay. But a subset of this is just, well, let's take a subset of the matrix, okay? And if it happens to be all numeric, a subset of this table, well, then this can just be a matrix, okay? So a matrix is a rectangular array, okay? That's what a matrix is. It has its rows, and it has its columns, okay? And you can access entries. So one use of a matrix, and we'll see other uses today as well, but one use for the data scientist is just a matrix is a subset of the representation of the data. Okay, so this, well, it can be this as well, this whole thing, for example, or I don't know, including this as well. Okay, so not a whole lot to the story, but just think of a matrix as a way of a place where we represent data. Again, this is important if we're dealing with numerical data. Okay, now in mathematics, matrices have scalars in them, and these scalars are placed in different locations. Each one is called a scalar. Okay, and the scalars in general mathematics should come from some field of numbers. Maybe it's a field of complex numbers, or maybe it's a field of real numbers, or maybe it's some other field of numbers. But we won't get so formal. For our purposes, these scalars will be real numbered, or maybe but they'll be the subset, which will be the integers. We'll actually formalize this a bit more in the units to come. So for now, just think of real numbers. These are real numbers on the number line. We'll also speak briefly about complex numbers as well. Okay. So that's a matrix. Now, looking at it in a slightly more formalistic way, a matrix is a rectangular array of numbers. Good. Okay. By the way, what if we didn't have just rows and columns? What if we had some other dimension here? What if I'd put some volume here? What is this thing called? Does anybody know? Or does anybody have a name for this? So a cube is, well, a cube if we look at it geometrically, but if I had some other matrix here and some other matrix there, so these, think of these as like cards sitting above each other. So that a matrix is this. But what if I'd stack a matrix on a matrix on a matrix? So what if this rectangular array would not just be two-dimensional, where I just have the dimension of the rows and dimension of the columns? What if I also had, say, this, which is the depth? Now this is already an m by n matrix, but what is this depth? A 3D matrix. Okay, so what people call it is a tensor. Okay, that finally the name tensor. Okay, so that's what you'd call a tensor. Has anybody heard of TensorFlow? TensorFlow? Put this in the chat. TensorFlow. So TensorFlow, a machine learning library. Okay, yeah. So a lot of machine learning, deep learning frameworks, etc., work on tensors, which are these generalizations of matrices. So just like a matrix, but you have other dimensions. Okay, but we won't really speak about tensors, and of course not on this thing called tensor calculus, which is also something we won't speak about. Okay, so we're back to matrices. So this is our m by n matrix. So this is the column dimension, this is a row dimension, this is a column dimension. Okay. And we can represent the jth column like this. This is the jth column, okay? So j here, I've stuck j, the index j into here, and I've pulled out the jth column, all right? Or I can represent the row vector like that. That's a row vector, etc. Now, people write these in different ways. So if you're actually writing text, it depends. So some people, if they actually write something like this within text, within mathematical text, then they treat it as a vector that's not a row vector. They treat it as a vector in general. And vectors are, in general, unless specified otherwise, should be considered as columns. Okay. So some people would write like something like this, and then put a transpose. And that's just because it will fit nicely in the text, but by that transpose makes it from a row to a column, but we'll get to transpose. Okay, so here's a matrix. Here's a matrix. a 2 by 3 matrix A. All right. Well, maybe now as you look at this 2 by 3 matrix A, I'll pause for a second and answer a question in the chat. There was a question. I'm just wondering, compare with the math in year 12 from how school has this been increased? So that's a good question. It hasn't been increased a whole lot beyond Math C, in the same way that the introductory courses of undergrad are not much beyond Math C. So Math C is in Queensland in Australia, what we call the kind of the high level of mathematics that you do in high school. However, this is university, so we kind of get a bit deeper and give things a bit more meaning. Okay. And so yeah, it is an elementary course in many ways. Okay, the programming aspect will add another dimension to it. And there's a nice question: is there a difference between round brackets and square brackets when we represent matrices? Generally, no. So some people use one, others the other. Typically, when we write, we try to be consistent. I actually like using these more. Okay, but one needs to for every text that you write, you should say what it means. Okay. All right. So the Aij's, so sometimes since this matrix has the notation capital A, we might denote its scalar elements by lowercase a, but sometimes other people would just do capital Aij. Let me just zoom in a bit, right? That's Aij. That's how we would do it. Okay. So that's the entry in the ith row and the jth column. Now, for this specific matrix, it was actually specified via a formula. Okay, so in a sense, the information which we have here, I'm going to scratch this out because it's redundant. Okay, so I'll scratch this out and you can tell me if you'd want, say, what did I just scratch out here? What is this entry here? So what does I equal here in this point? I equals, J equals, so Aij, which is defined for this matrix to be I minus J, what is that? Okay, so Aij, somebody says it's -2, and what is I there? So I is 1, 2 is the second row, and J is 1, 2, 3, 4, 4. So indeed 2 minus 4, I agree, is -2. Okay, all right. Is it -1? Did I make a mistake? I think it's -2. Okay, so that's, oh, it's a -1. So what did it do? Oh, 1, 2, 3, sorry. Okay, they're not 4 columns that I missed. So it's -1. So it's 1, 2, 3. 1, 2, 3. So J is 3. So 2 minus 3 is -1. Okay, thanks. All right. You could speak about the zero matrix, okay, and you just denoted 0, but of course there's not enough information if you just denote the matrix 0, like, whoops, sorry, if you denote the matrix 0 like this, there's not enough information. You need to say the dimension. So sometimes you might write it, again, it depends on what's the context in which you're speaking, but you might write 0, 3 times 2, for example. So we know that's a 3 by 2 zero matrix. And well, matrices are equal, and we just say A equals B if each of the elements are equal. That's what you'd expect, right? So if Aij equals Bij for all ij. When we get to the next unit in logic, then we'll see that a nicer way to write this is just the for all. Does anybody know the sign for all? Has anybody seen the symbol for all? We'd say Aij equals Bij for all. Yeah, like an angle like that, for all ij. And mathematics does involve a lot of slang because, for all ij, what do we mean for all ij? Well, we mean here for all ij within the dimension of A and B, okay? If matrices are of a different dimension, can they be equal? Can it? No, okay? So, for example, this matrix does not equal the 4 by 5 zero matrix. Okay, but you might not even, so that thing does not equal. Okay, but you won't even speak about it really. Okay, I know that this has not been the most exciting part of the course, trust me. We'll do k-means clustering today, which will be exciting. Okay, let's go and just do a bit of matrices in Mathematica. Now, who has Mathematica? Can I get some yeses if you have Mathematica running? We don't have to run it now, but just some to see if you have it installed. You need to be on the VPN to use Mathematica on the UQ VPN if you're using the UQ license. Good, I'm seeing some yes. Okay, and somebody's installing it right now, sad face. It might take a while. I've heard from a student or two, especially if you're in China and using the UQ VPN, it might take a while, so maybe it's a job for later. Okay, so let me look at the iPad. You could see my, let's see. All right, so what you have here is a Mathematica file, okay? I guess you cannot see my menu up there, the Mathematica menu, but that doesn't matter much. Now in Mathematica, I'm just going to start to write. I'm going to do 1 + 1, and then I'll do Shift-Enter. What does this remind you of? This thing with a Shift-Enter, what kind of environment? Hint, we met earlier today, many of you. Yeah, it's like Jupyter. Or let's say that Jupyter is like Mathematica notebooks. I mean, Mathematica notebooks, this Mathematica notebook existed forever, okay? And you can also write nice things in Mathematica, like, look, I can take 49, can do 49, and highlight that, and then I'll do Control-2, and it does a square root. So I do Shift-Enter, and it evaluates to 7, okay? So key point is, I'll put it as a comment, Shift + Enter evaluates. Now, in the first practical this week, you do have a practical this week, okay? So the practical on Friday, either see Amina at the scheduled time in UQ face-to-face if you're in UQ, but most of you are not. You'll see her via Zoom in one of the 2 times, okay? And in that practical, she'll do a whole bunch of things with Mathematica, okay? Just curious, are we allowed to use calculators? For sure. Yep, you can use calculators. Mathematica is a great calculator, but yes. You do not use Mathematica in the quiz, for example, but you'll use Mathematica in the assignments. Okay. Now, the reason we're using Mathematica is, let me just show you kind of, just motivate for a second why we're using Mathematica. So let me define, for example, the function f of x, which will be e to the minus x. Okay, I'll now just do Shift plus, what did I do? Sorry, Control plus Shift plus 6 did the exponent. Yeah, so Control Shift. Oh, just Control 6. No, Control 6. Okay. That's like the exponent. Okay, that's a call. So here's a function, okay? For example, and this e, what is e? E is e. E is a natural number e. Now, Mathematica is generally symbolic before it's numeric, so it didn't write e as a number, but if I'll do like, show me the numerical value of e, then this is a number e, okay? All right. So Mathematica is for symbol. And now let me just plot. So let's plot f of x, f on x, or I can call the variable u, u from 0 to 5, for example. Okay, so here's a function. Okay, and axis label, let's say x and f of x. Now, you'll do a lot of functions in this course. In mathematics, we typically denote functions with these round brackets, but the notation that Mathematica uses for functions is square brackets, okay? So this is a plot of x versus f of x, okay? Now, one of the reasons we like to use Mathematica is, let's say, in this course, one of the things you're going to learn later on, and it might be reviewed for some and might be new for others, is, let's say we look at this function and we want to know what's the area under the curve. What do we call the thing in calculus that will give us the area under the curve? So the area between the function f of x and the horizontal axis. Integration, right? Is this definite or indefinite integration if we're speaking about the area under the curve? Definite. Okay, if you answer too much, you'll definitely not wanting to do the course because that means you know it. No, I'm joking. That's fine. Thanks a lot. So that's definite integration. Okay. All right. So, you know, you can do calculus and do the definite integral of this. Now, this is going to be, we won't want the area from 0 to any point. We'll actually want to deal with infinity. So often infinity is interjected into mathematics, even though in the real world, few are the things that are really infinite, whatever that really means. But we often use infinity as an abstraction because we can look at this function, we can say, look, by around 5, f of the 5, and let me evaluate this as a number. Now, when you do this in Mathematica, this is postfix evaluation. Okay, it's just like the n applied to f of 5. Okay. So, you know, the function is very, very low. So, you know, if you want to find the area between under the curve between 0 and 5, you might as well find the area between 0 and infinity, or at least it's a pretty good approximation. So then we can say integrate f of u can be an x, but that's fine, of u going from 0 to infinity. So then I'll do escape, inf, escape, brackets, so I'll do that here, escape plus inf plus escape gave me. So what do you know? The area between 0 to infinity under this function was actually 1. Okay, I mean, it seems this function is just a very neat function, e to the minus x. Of course, if we'd scale it, it'd change a bit. Okay, now you will learn the calculus needed for this, which in this case would be finding the indefinite integral of e to the minus x and then doing an integral from 0 to L and then taking limit L to infinity. And that's what gives us this thing, which is called the improper integral. So that's just a preview of the things to come. Okay. So we like Mathematica for this reason, that we can use both numerics and symbolics. We like it in this course, not necessarily in all courses. What's a symbolic package in Python? Has anybody used a symbolic package in Python, by the way? So by symbolic, I mean, we can also do things like this in Mathematica. I can do a plus b to the power 20, well, let's do to the power 5, expand, and it expanded a plus b to the power 5. Has anybody done anything in Python? SymPy in Python does a bit of this. There's a question, can I scroll up? I'm not sure. Okay. Yeah, okay. So let's now get back to matrices. So before we do that, I don't think you can see that, but you can see my whole screen, but I'm going to go to what's called the style menu and put a section. So matrix operations. Okay, so I'll just put a comment here. Went to the format cell menu and chose section. Okay, it's not critical, by the way. Is there a guide? Yes, so there are plenty of guides, but you don't need to do a full course of Mathematica, okay? I'm showing you some things. You'll do some things in the practical, and then you'll discover them later on. So we'll share a bit more resources, but I actually do not want to bombard you with Mathematica resources, okay? So it's, and specific things that you'll need to do, we'll show you how to do. So the point is not to spend your whole semester learning how to use Mathematica. Okay, so matrix operations. So let's look at the matrix that we had before. And at first, I'll copy this matrix from the lecture material. I don't know if you remember what it was. Maybe somebody can, oh no, nobody can read it. Well, you can read it out to me. Does anybody want to read me out the matrix? We can actually have some voice in the class. The first row of this matrix in example 1. Oh, somebody wrote it. Okay, thank you. Casey. So 0, 1, -2, and 1, 0,
Oh,
1.
sorry, yeah, the last value is -1. I made a mistake, sorry.
Thanks a lot. Good on you. Okay, so look at how I've put. Thanks a lot. So look at how I've put this matrix A here. Okay, now in Mathematica, what we use. It's funny that Mathematica is a very mathematical language, but it actually uses notation that's different than mathematics. This curly bracket, okay, so I'll put a note. In mathematics, as we'll see next week, and some of you know already, curly brackets, yeah, this is curly brackets, are used for what? What are they used for? Sets. Okay, we'll spend quite a bit of time speaking about sets. Okay, that's what we use it. However, in Mathematica, they are used for lists. Okay, that's just you know. So now a matrix in this case is a list of two lists within it. This list is the first row, and this list is the second row. Okay. And if I now hit Shift Enter, I see the matrix A. Now this doesn't look very appealing. It doesn't look like a matrix to me. But what I can do is I can apply, for example, the function matrix form on A and see it presented nicely. Okay, or I could do also, I could have done A matrix form. That just applies the function matrix form to A just to see the matrix nicely. Okay. Now, let's use this definition. This matrix was a bit of a redundant, like having the data like this is redundant because we defined it as having the ith element as being the ith jth element, sorry, the ith j's element as being I minus j. So let's make another matrix. We'll call it A from def. And what we'll use is we'll use a table function. Now, whenever you want some help for something in Mathematica, you can do question mark, for example, table. And you'll get like a completion of what different functions that include the word table. And then if you do see that, you'll see a summary of table. And you can also go to the help and see, for example, the help local or web, and you'll see more examples on how to use table. You also see related commands. Of course, yeah, you need to know which commands to look for. But again, you'll see a few of the basic functions or commands built in. Okay, so for table, what I'm going to do is I'm going to do I minus j for I going from 1 to 2 and j going 1 to 3. And what I got here was A from def, which if I'll also look at it in matrix form, you can see it agrees with A. Okay, it agrees with A. Now I can ask A equals A from def, and I get a false. Why do I get a false? I'm not sure. But so actually I'm not sure. I'm not sure why false. But these two, A from def and A, are the same. Oh, sorry, I made a mistake here. So I think I made a mistake putting this one up here. Is that correct? So if I go back to the notes, this one should be -1. So we'll go up here and I'll put a -1 up here. And, you know, I'm just keying in the matrix. It's a -1. And this is A from def equals true. Okay. So two matrices are equal if each of the entries are okay. That's okay, Casey. Thank you. All right. I know this is not super exciting just yet, but by the end of the day, we'll actually see a machine learning algorithm. Okay. I promise we'll actually bounce a bit forward to see a machine learning algorithm. Let me quickly go back to the lecture notes, and then we'll take a break just in about a minute. So what we're going to do is always 50 minutes, 10 minutes, 50 minutes, 10 minutes, 50 minutes, 10 minutes. Okay. Well, last 10 minutes are not 10 minutes. The last 10 minutes we finish. So 3 chunks of 50 minutes. Okay. Matrices as images. So the thing is that if you're looking at a monochrome image, by monochrome, I mean black and white, but maybe not necessarily black and white, an image with one color dimension. So not an image like you're seeing me now as an overlay of R, G, and B, red, green, and blue. That's a tensor, okay? That's not a matrix. But if you just look at an image that has one color, then, for example, this image of the digit, then you can represent it via a matrix, okay? And a lot of algorithms in machine learning treat images as matrices, and then if we go to color images, they go to tensors. Okay, so that's the only point of matrix as an image. All right, so just after the break, we'll deal with matrix operations, and we'll move on. Are there any questions before we take a break? Okay, so I'll see everybody in pretty much exactly 10 minutes in the round hour, and well, except for the folk in India, it's not the round hour for you. You live with a half-hour difference. Okay, see you guys soon. Bye-bye. Oh, was the dog an Australian Terrier? The dog I showed earlier today? No, Dash is Kelpie mixed with Border Collie. Thanks for asking. Okay, see you in a bit. Bye. So we'll start in 5 minutes, but if anybody has some questions, we can use this time. Also, private questions. You feel free to send me some private questions in the chat if you have, if you're not sure if the course is for you or anything else related to the data science program.
Sorry, you mute yourself.
Sorry, thanks a lot. Okay, I don't know how that happens, but thanks for telling me quickly. So if you go here to Blackboard, this we sent on this message. This tells you how to access Mathematica. Okay, so follow those instructions. I think most students have been able to do it. If you have trouble there, drop us a line. Okay, you need to be on the UQVPN, etc. You follow the instructions and you get it working. Okay, more questions? Oh, thanks. And Ajoy dropped that in the chat for everybody. All right, let's continue. So what I'm going to do is stop the share here and continue with the notes. Toot, toot, toot. Somebody asked me about Dash the dog. Dash, you need to leave the room. Sorry. See you. Okay, so matrix operations. So when we learn basic mathematics, we know how to add numbers, right? We know how to add numbers, but we can also do that with matrices. Not with any two matrices. Matrices need to be of the same dimension to add them. And this formula here defines the way we add a matrix. Okay, it's very straightforward. So the ijth entry of the matrix, which is the sum matrix. So if you'd call this, if you say C equals A plus B, so what we're saying is that Cij, the ijth entry of C, is Aij plus Bij. Okay, we just add them entry-wise. I mean, doing element-wise is the most basic thing you'd expect. And you can actually, this figure is not relevant for that, but even if you, for example, look at my image. So Zoom has put behind, ignore the fact that it's a color image. So it's not just a matrix. So it has actually 3 layers. Assume you're just seeing me in black and white. And maybe somebody here is colorblind and you're just seeing me black and white. So you're missing the UQ branded purple logo behind. That's okay. All right. So what UQ has done is done a superposition of my, what Zoom has done is done a superposition of my image and the background image. Okay, so if you had my image with white background behind and the background image and you added them, that's what you see. It's not exactly true because it actually replaced some points. But what I want to say is that you can add 2 images and see the result. Okay. All right. Now some properties of matrix addition. So clearly A plus B equals B plus A. I mean, that is because the addition of the numbers is commutative. So that's called commutativity. So the addition of the matrices is commutative. Okay. And what is this property called? If this property was called I might be misspelling it, so sorry if I am, commutativity. What is this property called? It's called associativity. So what it means is that, well, if we want to add the matrices A plus B, and we first look at this sum and then add to that the matrix C, then it's just like first adding B plus C and then adding to it the matrix A. So it's this property that allows us to write without ambiguity. So ambiguity means when things have multiple meanings, but we can write without ambiguity something like A plus B plus C. Okay, if matrix addition would have not been associative, we couldn't write this. But since it doesn't matter if we first do this or if we first do this, then we can write that. And that again just follows from this property of the scalars. Okay, so no surprise there. Now comes this thing called scalar multiplication. All right, so let A be an m by n matrix. Okay, so oops, sorry. A is an m by n matrix, and what does this mean? What did I just highlight? How do I read this thing? What am I? So part of the thing of the language of mathematics is to read things and just be able to say them. And I was going to say something. What was I going to say? what was I going to say with this thing? And let, or, you know, A is an n by n matrix, and I got stuck. Maybe Zoom is stuck. Nobody knows. Somebody would know. So this other variable is a real number. What do we call this variable? Alpha. Yeah. Okay. So if you haven't dealt with Greek letters, you'll be dealing with them soon. Alpha, beta, gamma, delta, epsilon, etc., eta, kappa, psi, Greek letters. Okay. And what we mean here is that alpha is an element of the set of real numbers. Okay. So this just says alpha is a real number. So it's a scalar. It's a real number. Okay. We'll deal with this notation more in the units that will come. Okay. So belongs to is an element of, right? So belongs to is synonymous with is an element of. Is it right to say alpha is a subset of the real number line? So that's a subtlety. No, it's not actually. Okay, it's not alpha as a subset. It's an element or it belongs to. But we'll get to that in the discrete math. Okay, so you know, let A be a matrix, and here's a scalar. So now we have some new matrix, and this new matrix we'll call it. Yeah, it's a constant, but sure, it can be. All right, it's a matrix alpha A. And what we mean here is that we took every entry of A and we scaled it by alpha. Okay, so we multiplied it by alpha. Okay, so the way you read this is the ijth entry of this new matrix is just the original ijth entry multiplied by alpha. Not too much to this. Okay, so once we have that, we can immediately say what the negative matrix is. Okay, because this is just taking alpha equals -1 and multiplying it by A. Okay, so that immediately gives us matrix subtraction. So matrix subtraction is the addition of the -1 scaled matrix B to the matrix A. Okay, all right. I assume there's nothing special there, but that's so you can multiply a scalar by a matrix, and you can think of it that scalar, if that scalar is positive. So let's just think a second. So if alpha, let's just take some values for alpha and just tell me in words what it does. What if alpha is greater than 1? What's going to happen to the entries of A once we scale it? If alpha is greater than 1, what's going to happen to the entries of A? I'm talking about this case here. If alpha is greater than 1. Well, then they're going to grow, right? Because every entry of A is now going to be multiplied by, say, 1.7. So it's going to grow by 70%. What if alpha is in the interval 0, 1? Okay, what's that going to do to A? It's going to shrink. Yeah. Am I not clear, or maybe it's too trivial? Okay, I don't know if the yes is too trivial or not clear, or not clear. Okay, and if alpha is negative, you're going to change the sign and maybe grow or shrink. Okay, thanks. Okay, so here's an example. Here's a matrix A, here's a matrix B, here's a matrix A plus B. So all you need to do is you just need to look at a specific entry. For example, this entry 5 is this 6 plus this -1. That gave you this 5. Okay, here's A minus B, etc., etc. Okay. When you write A plus A, you can represent it as twice A because it's scaling the matrix A by 2. Okay, so A plus A is just like twice A. All right. Now we're getting to the good stuff. Matrix multiplication. So matrix addition and multiplication and kind of scalar multiplication of matrices is maybe sensible, but matrix multiplication, which I'm sure you've all seen, but maybe some of you have not used for a while, or maybe one or two has not ever seen. Matrix multiplication is a new operation that gives us a matrix, which is the product of the two matrices. Okay. Now, by the way, we'd want all these operations to generalize the scalar operations. Okay, so of course, if I just have the number 17, that number, you could think of it as it's a scalar, but you could also think of it as a 1-by-1 matrix. Okay, that's the number 17. Okay, it's a scalar and it's a 1-by-1 matrix. So I'd want addition, multiplication, and scalar multiplication to all generalize it. Okay. So here's how matrix multiplication works. So there's a whole lot of characters on the screen, and there are many different ways to actually view matrix multiplication. Even though it becomes a bit of a trivial thing, there's actually a bit to it. Okay, so you have a matrix, an M by N matrix, and what I'll do, I'll actually paint these entries M by N, and you have another matrix here, which is N by R. Okay, so you have three numbers of the dimension, M, N, and R. Okay, so let's just take the M bit, the M is here. That's the number of rows. The N is here. And here you've got the N. N, yeah. And here you've got the R. All right. So important is that this N will equal this N. That's why they're both called N, and I colored them in the same way. Okay, so you want this dimension to agree. And this matrix here is a matrix A, and this is a matrix B. I'll erase that just because it's a bit messy, but that's a matrix A, and that's a matrix B. So our matrix, which is a product A times B, AB, we just write AB. That's, you could have written A, maybe dot B, but it's not so typical. Just put AB. Okay. All right, so that dot can be a bit confusing. You just put A times B. Okay. Is a matrix that gets this M. What is this? This M dimension and this R dimension. You see that N dimension, that intermediate N dimension, this guy, oops, sorry, don't want that. This guy here vanished. All right. So before we even move forward, and how this is done, let's just take here, if the matrix A is 1/3 and the matrix B is 3/2, look, the joint dimension, the N is just 3. Okay, and what we're going to get, the result here is going to be I'll paint it with these colors, is going to be a 1/2 matrix. Okay, so you'll get a 1/2 matrix. All right. All right. By the way, this 1/3 matrix, you can call it's a row vector, but we haven't really spoken about vectors. So you can treat vectors as individual objects of their own type, or you can treat vectors as matrices where one of the dimensions is 1, where either the rows or the columns are 1. Okay, that's what a vector is. Okay, back to the matrix multiplication. So how is this done? So it's all given in this formula. Okay, and this is the formula for the i-kth entry of this matrix. I-kth entry of this matrix. So what we're going to do is we're going to run on row I and on column K. So row I of A, this is a matrix A, yeah, here's A, and column K of B. Okay. So, and we're looking for the i-kth entry of this matrix here, this result. So I'm talking about the i-kth. So this is now the i-kth entry. I-kth, I say kth. Okay. All right. So what do we do? What do we do? What we do is we take the inner product, which we haven't spoken about, but here it is, of these two vectors. This vector here, this row and this column, what do they have in common? They're both of length n. Why are they both of length n? They're both of length n because n is required to be, that's the only way matrix multiplication works. N is their joint dimension between these two matrices. Okay. And what we do is we then, let's scribble on this more, we're going to take this AI1 and B1K, AI1 and B1K, multiply them. And then we're going to take, let's take a slightly different color. We'll take AI2 and B2K, these two guys there, and multiply them. And we're going to multiply, and add, and we're going to get this entry. That's how we're going to do it. Okay. So that's the most basic way to look at matrix multiplication. All right. Now, if matrices are square, what does it mean that a matrix is square? How would you describe what's a square matrix? What's a square matrix? M by M, right? So number of rows and number of columns. So if you take two square matrices, they have to be of the exact same size, okay? So let's take a 10 by 10 matrix A and multiply it by a 10 by 10 matrix B. What is the result? What's the dimension of the result? It's going to be a 10 by 10. So that's going to be the matrix C, say, which is 10 by 10. So I just want you to think, looking at this formula, how many scalar multiplications do we need to do to achieve this C? So how many scalar multiplications do we need? So this is a scalar multiplication. This is a scalar multiplication. This is a scalar multiplication. How many scalar multiplications do we need to do to achieve this C? Okay, so I got 100. I got 1,000. 1,000. Are we settled on 1,000? 1,000. I see 100. Somebody. Okay, so can somebody from the 1,000 convince somebody from the 100, or vice versa? So first of all, how many entries are there? How many entries are there here? There's 100 entries. But for each entry, we need to do an inner product of 10 multiplication. So just like that, matrix multiplication is, you'd call that an n cubed operation. So if you take an n by n matrix, okay, two n by n matrices, of course, this would slightly vary if they're rectangular, meaning, you know, if they're m by r, but you'd still need that inner dimension to agree. But in general, the time it takes to multiply is, you can call that the order of n cubed. It's kind of interesting that there are actually some computer science algorithms that know to do it in a smarter way for general matrices that can do it in about n 2.3 or something like that. Okay. But that only becomes efficient for huge matrices, and that still hasn't been really used in data science per se. Now, often matrices will be sparse. I'll answer the question in a second. Oh, okay. So there's a great description on the chat. Right. Thanks for the description. What does it mean that a matrix is sparse? I'll write the word sparse. What does a sparse matrix mean? Sparse. What does it sound like? Sparse. So a sparse matrix is a matrix that actually has a lot of zeros, okay? Many zeros, okay? That's a sparse matrix. So for sparse matrices where you have many zeros, then you can do better than this n cubed. Okay. All right, let's go back to Mathematica and just play a bit with matrix multiplication and also plotting some matrices, and then we'll actually move to something different. We'll pause with the linear algebra bit just for a bit and move actually to k-means. Any questions more? Just yet? Okay. So Mathematica here. Now this file is called Untitled 2 for now, but that's okay. I'll just save it quickly. Okay. It's now called week 1. All right. So let me create a matrix of random entries. So what I'm going to do, I'm going to use a function rand. So look, if I just hit rand, notice by the way that functions in Mathematica all have their name starts with the capital. Okay, so It's all capital case. That's a naming convention with a new capital when every word starts. It's kind of, sometimes this is called camel case, although camel case would often have the first letter lowercase. Okay, so there's a function random integer. So I'm not sure how to use random integer, so I'll do this drop down and I see a random integer. If I give it these two curly brackets here, it gives a pseudo-random integer in the end I min to I max. Okay. So pseudo-random integer, that means that the computer is not actually generating some random number from the atmosphere or from some protons that are randomly flying or something like that. It's actually using an algorithm, but this algorithm creates noise, well, creates a sequence of numbers in such a noisy way that they seem random. Okay, so you'll work a whole lot with pseudo-randomness, which is just kind of generated randomness in a computer throughout this degree. So let's say if we take a random integer between 1 and 7, here's a random integer, okay, and here's another random integer. Now, what I'm going to do in Mathematica, I'll just to make this short, I'll just do R capital I, and I'll do this colon equals. And this just defines whenever I do Ri, it's going to evaluate the right-hand side. So look, I can do Ri, and I can do again Ri. It's just my random integer. Okay, so I want this just to be able to generate matrices. So if I do A now, is going to be it. So, and let's make the constants. Let's make M equals 3, N equals 5. What was the third one? I think it was R equals 2. Okay. So let's take the matrix A to be a table of random integers, Ri. Mathematica is, of course, case sensitive, so I need this lower case R and capital I. Okay. And if I just put here M and N, it's going to create, oh, sorry, I didn't run this command, so it doesn't know what M and N are. He'll create the matrix form. Okay, so if I do this and if I put a semicolon suppresses output. Okay, that's what the semicolon does. Okay, just like in MATLAB if you use MATLAB. And I can do then a matrix form just to see it nicely. So this is a matrix A. Let's do the same with a matrix B. Actually, lightning and thunder outside here in Brisbane at the moment. Matrix B. So let's make the matrix B dimension n by r. Okay, and let's delete this and do B matrix form. Okay. Now, can I multiply A and B? Can I multiply A and B? Look at A and B and their dimensions. Is matrix multiplication between them defined? Okay. Well, can I multiply B and A? Can I multiply B and A?
No.
No. Okay. So when I said multiply A and B, you assumed I meant A times B, right? And I cannot do B times A. Now, matrix multiplication is in general not commutative. So scalar multiplication, 5 times 7 is 7 times 5, right? But matrix multiplication in general, no. Even if the matrices are square. Here it won't even work because of the dimension. But let's see it. So the way I do it in Mathematica is I put this silly dot, okay? So dot is matrix multiply. Now I got here, let's call this a matrix C. Okay, and let's look at it, just ask it to present it nicely. By the way, matrices are, Mathematica is, oh, sorry, let's call it, C is like a protected word. Key in command in Mathematica, we'll call it CC, okay? So just CC. Okay, so we got a matrix of dimension. What's the dimension of CC? What we can do is we can do, I think, the size function or dimension or length. I'm actually not sure how to get the dimensional matrix. We can do length of C. If we do length of C, of CC, it'll just give us 3. It'll just give us the first dimension because matrices are nested list. I'm actually not sure how to get the dimension just yet. Okay, so we got a 3 by 2 matrix because we've kept the row dimension here and the column dimension here. Now, what will happen if I do B dot A? What's going to happen here? what's going to happen with B dot A? And let's see. Error.
Yeah.
Error. Now the error Mathematica tells us is say, hey, these tensors, because it's expecting things that are slightly more general than matrices. Matrices are a special case of tensors. But say the tensors have incompatible shapes. Okay. Will this work? Nope. Okay. And just to see that matrix multiplication is not commutative, let's take the matrix A, which in this case I'll do 1, 2, 3, 4, 1, 2, 3, 4, and take the matrix B. So now I'm defining, and I'll do this 2, 0, 1, 2. Okay. Now here I can do A times B, right? And I'll just see it immediately in matrix form. And I can do B times A because they're square, right? So I can do the inner dimension would always agree. But most of the chances are that these two matrices will not commute, meaning that A times B is not B times A. Okay. Different when flipping order. Okay. All right. So that was just a bit of matrix multiplication. Now, it seems maybe a bit odd. Why do we need matrix multiplication? I mean, there's so many ways that matrices can be, they could have thought to create these things. It seems a bit arbitrary that you take the rows and the columns and you do this thing. So why do we need it? So there's actually so many uses of matrix multiplication, and you'll get. I'll move now to the visualizer. And you'll get to it much more in Math7502, but also just in applications. So who's here excited about neural networks, for example? Somebody? Did somebody want to study to data science for deep learning or because of the AI revolution? And okay, you've even done it in your undergrad, great. So let me open here a new sheet. Okay, so when we look at, for example, a deep neural network, and many of you might not know exactly what that is, but you may have heard that, for example, deep learning is that branch of machine learning, and that's pretty much what people kind of called artificial intelligence lately. It's something that you're going to study later on in this degree, and we'll speak about it a bit in this course. So if you look at a deep neural network, what's happening there is actually inside is a combination of many matrix multiplications together with nonlinear operations. Okay, so it's not just matrix multiplications and additions later on. There's also some nonlinear operations. So the whole concept of neural networks is basically matrix multiply plus nonlinear scalar operations. Okay, so that's, for example, one use, but we'll get for a fundamental use for a more kind of historical one in a second. You've raised hand. Yicheng, you've raised hand. You have a question? Just shout it out or print it, or do you want to say it, Yicheng?
Yes.
Yeah.
I'm also wondering, as for the matrix multiply, do we during the exams or for the assignments, we are able to use like a calculator or Mathematica as for the tools to help us do the calculations, isn't it?
Not a problem. So the quiz and exam, you do not use Mathematica, but you won't have extremely exhausting matrix multiplications or matrix inverses or things like that. Okay, that's for the quiz and the exam. For the homework, you can certainly use Mathematica. Okay, so
okay.
in terms of computing calculators, no, you won't be able to use a calculator that computes, but we won't give a quiz that focuses very heavily on doing a whole bunch of multiplications.
Okay, I see.
Yeah, did that answer?
Yeah.
Okay, thanks. Okay, there was another comment in the chat, convolution question mark. So yes, the operation of convolution is a linear operation, and in general, any linear operation can be represented via matrix multiplication. You'll see that in Math7502. But for now, let's just go for something very simple, and let's just look at the system of equations. 2x plus 3y equals 7, and 5x minus 2y equals 4. Okay, and this might look a bit boring, but many things in the end of the day amount to linear system of equations. So often, by the way, if your systems are not linear, they still, we can linearize them at certain points, and then we get, so this is linear equations, okay? Linear equations. And you've learned this long before, you know, you have your x-axis and your y-axis, but of course we could have had more variables if you'd like. And what you're seeing here is, I'm not going to draw these lines to scale, but there's basically one line here which is associated, say, with the first equation. And ideally, if I didn't pick my numbers too bad, there's a different line here which is associated with the second equation, okay? And then the point of the intersection is the xy point that satisfies both equations, okay? But of course, I could have add a third variable, say plus 5z, you know, plus 20z, and then it's no longer lines, but rather hyperplanes in space, okay? And I'm still looking for the point x, y, z, if such a point exists, or if such a unique point exists that satisfies these equations. So the point is, how can I represent the system of equations via a matrix and matrix multiplication? And I'm sure you've all seen this before, but it's something I just need to show you. But before that, let's just think about multiply matrix by vector. Okay. So what's a vector? Well, a vector is a matrix where a column vector, so column vector is, if you'd like to think of it this way, you could think of it as an n by 1 matrix. And a row vector is a 1 by n matrix. Okay, if you'd like to think of vectors this way. Let me just add a blank page here. Oops, sorry, did I stop my share? I think I did. Let me share it again. Don't know how that happened. So who's here in Brisbane? Is somebody here in Brisbane at the moment from the class? Are you having a big storm? Because here where I am on the south side, yeah?
I am.
Okay, good. Yes, so we do have storms here in Brisbane. But we still have internet. That's good. All right. Pretty bad, but we're hanging in there. All right. So if you're looking at, say, multiplying a 2 by 2 matrix, let's just call this matrix A, B, C, D, times, I'll now multiply it by this matrix UV. Okay, so that's a 2 by 2 matrix, and that's a 2 by 1 matrix. The important thing is that this 2 and this 2 are in agreement, and I will have a result which is a 2 by 1 matrix, which is a vector. Fine. So that's how you multiply a matrix by a column vector. Sometimes you would call this applying. I'm applying this matrix. I'm applying this matrix here. I'm applying it to this vector. And the reason that sorry, now my Mathematica sent me a note. Just one sec. Sorry. It's just that I got a pop-up that Mathematica is not happy because it needed the license key. Maybe I got kicked out of the VPN, or maybe UQ's VPN in trouble. But I think you can still see me because I can see myself on the iPad. That's what's important. Okay, so I'm applying this matrix on the left, applying this guy to this vector. Okay, and this is the result of the application. Now, of course, we can still use the rules of matrix multiplication just like we did. The way we do it is we multiply this row by this column. We do the inner product of that, and this will give us this guy. And similarly, we multiply this row again by this column, and this will give us this guy. Okay, that's how we do it. Okay, so just to see it, I just see that my Mathematica kicked me out. I'll see what I would have done this symbolically, because one of the nice things that nice about Mathematica is we could do it symbolically. But just to write, let's just write this here. So then I would have this here would be AU plus BV, and this will be CU plus DV, right? Okay. So once you believe this paradigm, and this is not specific to this 2 by 2 case, right? You could have in general applied a square or rectangular matrix onto a vector. Okay, so in general, you could have, and by the way, you'll see this in Math7502, anything that's a linear transformation can be represented in this way. So you're taking the vector uv and linearly transforming it according to the linear transformation described by this matrix, which in this case has entries A, B, C, D. Okay, so let's go back to this system of equations and write for yourself a second this system of equations, write it in the form of a matrix, a 2 by 2 matrix, times the vector xy equals some vector here. So go ahead and fill for yourself out what this number is, and 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 this number is for this system of equations. So that represents this system of equations in matrix form. Okay. As you do that, I'll get my Mathematica working again. Let's see. Sec. I'm just getting my Mathematica working. It's actually important to have it for the last part of today's lecture. I'll be with you in a second. Is anybody else got kicked out of the UQVPN at the moment if you're using Mathematica? You don't have to use Mathematica during the lecture. You don't have to do what I'm doing live. So what happened on my end is that the UQVPN, the virtual private network, kicked me out. And unfortunately for Mathematica, we do need to be connected to the VPN for the license server. And then Mathematica kind of basically crashes. So I've reconnected to the VPN. Zoom sailed through this smoothly. Okay. All right. So I've got some answers. I'll just okay. So you've done this representation. Great. And let me share screen on my. You know what, just before I share screen, so let's just answer this together. So as you wrote, you have a 2, 3, 5, -2, and a 7 and a 4, right? So the nice thing about this matrix representation of a system of equations, this system of equations may be fine when you have 2 by 2, you know, 2 equations and 2 unknowns. But the fact is that in data science and in applied math, but certainly in data science, you have thousands of equations and thousands of unknowns, and then you could still represent it in this very succinct form. Okay. So that's one great strength of matrix multiplication. So in fact, what you'll often see is just a general system of equations. You might write it as AX equals B. These four characters are extremely powerful, this combination of these four characters, A, X, 0 equals, and B, where what you would often get is that A is some general n by n matrix, maybe it's 100 by 100. B is 100 by 1 vector, X, a vector of unknowns. Okay, so X would now be your vector that had before X and Y, but now you'll just call it, for example, you might just call it X1, X2, up to X100. Okay, that's what you'd call the scalar elements of X. And B is also 100 by 1, right-hand side. Okay, so that's the general system of equations. And I'm sure some of you have done Gaussian elimination and things like that. You'll do some of this in the next course, Math7502, but it actually won't be as boring as those classical linear algebra courses in the next course. It'll be much more computational with applications. But the point is that here you have matrix multiplication between A and the vector X. Okay. All right. Any questions, thoughts? All right. Yeah.
Sorry, sir. I got another question from the matrix that comes before. Could you please scroll the board up?
Sure.
Yeah, this one in the 2x one, 2x plus 3y. Scroll a bit down, just like a deep learning session one. In that matrix, just don't understand how we get the answers. Like
Oh, yeah. Go ahead. So you're asking why is this equivalent to this?
yes, that's right.
Not a problem. So if we would take this, so it's all about yeah, okay, that's okay. So it's all about taking we're multiplying this matrix here by this matrix, which happens to be a vector. Okay, well, multiplying the one on the left by the one on the right. Now we know that when we do that, then we know what this entry is going to be. This entry is going to be this x times this 2 plus this y times this 3. Okay, so we're actually saying 7 equals x times 2, or 2x if you like, and 3 times.
Yeah,
okay,
I see it now.
Very good. Okay, so yeah, I mean, it's one of those things, if you haven't seen it before, you actually need to think about it for a bit, but it's a way of representing this system of equations as this matrix vector equals vector multiplication. And yeah, it's very powerful. Okay.
Thank you very much.
No problems. Yeah, ask as many questions as needed. Always good. More questions, thoughts? Okay, so there are some properties here of matrix multiplication, and you know what? We'll just look at them very quickly, and then but then I want to move to the next part of the lecture. That'll take the whole last hour, and I think that should kind of liven things up a bit as well. All right, so matrix multiplication happens to be associative. Okay, so that's the way it is. So you can AB, if you first multiply AB and then you take the result and multiply it by C, then that's like taking A multiplied by the product BC. Okay, and you need to write it out to see why it works or to prove it. Okay, but the fact that it's associative, I mean, with addition it was simpler, but here it's also associative. This fact allows us then we can write without loss of without ambiguity A, B, C, right? So it basically doesn't matter if we put the brackets first here or if we put them first there. That's associativity. And there's also distributivity. Okay, so you certainly know distributivity for scalars. You know that A times B plus C. I mean, most of middle school mathematics is based on A times B plus C. These are just numbers A, B, and C. Okay, scalars is AB plus AC. right? I mean, you've done this many times in your life. You've done this, and that's how you distribute it. Okay, that's a distributive law. That's actually one of the assumptions of the field of real numbers. Okay, it's just a natural thing that happens in. Okay, now the same happens when you combine matrix multiplication and matrix addition. However, remember with matrices, we need to remember which side. We can't just flip. So here, when you're adding the matrices A plus B and multiplying that by the matrix C, then you can distribute the multiplication. But make sure that this will be AC and BC. Okay, C stays on the right. Okay, and here you have A times B plus C, and A stays on the left. So you've done the distribution, and A stays on the left. Okay. Keep in mind that if the product of two matrices is 0, it doesn't mean that one of them is 0. Okay, this is very different than numbers. Okay, real numbers. If you have two numbers, if you have numbers, x times y, the scalars x times y and x times y is 0, then either x is 0 or y is 0, or they're both 0. But with matrices, look, for example, the product of these two matrices can be 0. So just for yourself, let's just verify, for example, this 0 entry. Okay, for this 0 entry, what we'll do is we'll multiply 2 times 2 times negative 1 times 1. So 2 times negative 1 is negative 2 plus 2, and that's how we get this 0. And you could see the other zeros as well. Okay. All right. So what I'm going to do now is just move. We'll get back to this part of the unit next week probably, or at the end of today if we'll still have time, to dealing with matrices. But I'm actually gonna, so I'm pausing right here before transposition, just because this is a lot of details. Now I'm seeing stuff in the chat, VPNs, global protect, etc. But actually the people that are chatting about this always chat. That's good. Chat is good. Please send me an email about global protect, because I'm actually interested about the email that you got from UQ for VPN. Okay, so if somebody can send me the formal email you got from UQ about your VPN, I'd be interested, because earlier today a student told me that things are very slow downloading from the VPN. Okay, so I see all this chat about VPNs. I use a Cisco VPN or something like that. Okay, Cisco Anytime Connect. For UQ. Okay. So I want to stop for a minute with matrices and go to their little brothers, vectors. And by the way, mathematics is kind of funny because you can treat vectors as special cases of matrices, but you can also treat matrices, and you'll see this in a more advanced math course, as special case, as elements of a vector space. So matrices in themselves are vectors. But when we're speaking about vectors in this course, what we mean are typically these things that have entries here, x1, x2, x3, up to say x25. This would be the vector x. Okay, so this vector x, if we don't say anything else, it's a column vector. Okay, and we might call it a 25 vector because it has length 25. Okay, we can also write it as x1, x2, x25, and put a transpose here, even though I skipped the transpose, but that's okay. Transpose just does this. Okay, into a matrix it does this. Okay, what it did to this matrix is did this. It went from there, oh, like that. Look, it was like this, and it went like this. Oh, you can't see it. Zoom made it disappear. Okay, so that's what you can do. Sometimes you can just call it x1, x2, x25. You can call it a 25 tuple. So we'll actually speak a bit more formally about tuples later, but it's just an ordered sequence of numbers. Come on, that's a vector. Okay. Now, for data science, if you look at an individual, I'm an individual. My name's Yoni Nazarathi, okay? You can take numerical values from my life and put them in a vector. For example, here x1 would be my age, 47. Okay, that's my age. It's prime number. Okay, and this would be my weight, 110 kilograms. Too much. Okay, and this would be my height, 182 centimeters. Okay, so in this 47 years, etc. I mean, there's probably quite a few numbers you can put about me. Okay, forget the categorical data. In this course, we're speaking about numbers. Okay, so a vector is often an observation of an individual or a subject, or maybe you're not speaking about people, maybe you're speaking about cows in a cow factory, well, in a cattle farm or whatever, or maybe about cars or something like that. But a vector is a sequence of observations, and these guys, from a data science perspective, you might call them features. So that's the first feature. My first feature is my age, my weight, my height, maybe x4, the number of kids I have, which is 3. So some of these are integer values, and some of these, I mean, you can't have 2.7 kids, right? Well, maybe you can. I'm not sure. Okay, let's keep kids as integer. Okay, so there's 3, etc. Da, 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 da. That's a vector. All right. Now, when you treat vectors in this way, you're thinking like a data scientist, really. Now, alternatively, you might have seen vectors before and have drawn things. Oh, I see, I need to take a break, but have drawn things like, here's a vector. Okay, that's a vector. Then you're pretty much thinking like a physicist. Okay, so a vector has like a direction and a magnitude. Okay, you only draw them like this in the space R2 or R3, really, if you draw them, because, they're vectors in space. Something is flying and it has a vector of trajectory. So these are kind of 2-dimensional, 3-dimensional vectors, but you can think of them as this would be your origin 0, 0, and this would be your x1 and x2, and that's the vector x1, x2, for example. That's now an element of R2 of the plane, okay? Or you could have maybe put it in 3-dimensional space, added another coordinate. But we'll mostly think of vectors like that. Now, what we'll do just after the break, we'll speak about the magnitude of vectors, namely their norm, and then we'll spend the rest of the time having fun with an algorithm called k-means, which deals with the data science use of vectors. So we're actually leaving the matrices until next week, anyway, that's what we'll do. Any questions? Yes, clustering, that's what we'll do. Any questions before the break, of which I've stolen 2 minutes from you? So enjoy the break, 8 minutes. See you in 8 minutes. No, we will not deal with vector spaces and subspaces. That is in the next course. In this course, we only do very basic things with vectors and matrices. Okay. Enjoy the break. See you in a bit. Yes, next course is Math7502. And that's in semester 2. All right, I am back. We'll start in a minute or two. Any questions, informal questions before we pick up? All right, 7 in the evening in Brisbane. We're still not flooded, although it's raining big time. All right, so we're speaking about vectors. We're going to have a fun last 50 minutes for today. I know for many of you it's been a very long day, especially those who did data 7001. So thanks for hanging in there. All right, so I was just saying that as a data scientist, you can think of a vector as a sequence of observations for, for an individual. This is just metaphorically speaking, but actually not. So a lot of the algorithms that deal with data just treat kind of a vector as one particular observation. And often with this number 25, maybe 25 is going to be a very big number. Maybe it won't be 25. It'll be like 800 or 8,000 or 100,000. Then it's high dimensional data. Okay, high dimensional data. But let's actually, I said I revealed the sad fact that I'm 110 kilograms and just a natural fact that I'm 182 centimeters. Let's just speak about two-dimensional vectors just to make things easy, and we'll try to make a point with this example. So I'll go back here and I'll just go to the vector x, and we'll call x 110 and 182. And we agree that this is the weight in kilograms and the height in centimeters. And I just want to ask if somebody doesn't mind revealing, does somebody here, is there a person Y here with a weight and a height that's kind of like mine? Kind of. Anybody want to say there? If somebody is kind of in the ballpark, if you think you are, just reveal your Y. Or maybe if you want to make believe you're behind, just invent any weight and height and tell me what it is. But somebody give me a Y. Okay, we've got, well, so somebody's showing off 85 and 183. You're just trying to show that your BMI is much better than me. But okay, we'll take it. Fair enough. Okay, I'll take the first. Thanks for sharing. So we've got 85. That must be the weight, and 183. Okay, so I am X, and the person who said that is a Y. Y, you're kind of much fitter. I mean, I need to work on this, but that's not for today. Let's just leave that. All right, so how do we measure the difference, the distance between X and Y? So first of all, because we just narrowed, we're not speaking about 25 features, or 25 coordinates of a vector, we're just speaking about 2. Of course, we can plot these vectors, right? We can take here the Euclidean plane, we can call this X, let's just call this the weight, okay? And the height, okay? And I am at 110 and say 182. These numbers are not to scale. And there is a person at 183 and 85. So let's do that in red. 85 and 183. So that would be, I guess, something like here. Okay, so at 183, which is just like 182 and 85. Okay, so this is the Y vector, and this is the X vector. So how do we measure the distance between X and Y? Now, actually, a lot of data science and the mathematics of data science and the algorithms having to do with that are about distances between vectors and are based on that. And there are actually many different ways, and you'll see it in more advanced courses. You'll speak about different norms or different distances in general. But the most basic way is indeed, as was written in the chat, is a Euclidean distance, okay? So what we can do, we'll say the distance is, I'll just do it manually for a second. I'll just do 110 minus 85 squared plus 183 minus 100, or let me just be consistent here. So I'll do 182 minus 183 squared, the square root of that. This was discovered by humanity, well, the Euclidean plane much later, but this thing, which is based on Pythagoras' theorem pretty much, was discovered 2,500 years ago. Okay, so what we did is we looked at this difference vector, okay, the vector x minus y. We called that, let's just call it the vector d, for example, okay? And what we did here is we looked at the norm of d, okay? So if that vector d has elements d1, d2, so what we did, the norm of d, and in this case is the Euclidean norm, is the L2 norm, is what we did is we did d1 squared plus d2 squared, okay? So this is, say, d1, and this is d2. Square root of that. Okay. So in general, when you have a vector, say d, which maybe has entries d1, d2, up to dn, then the norm of d is sum I 1 to n, and we're talking about the L2 norm or Euclidean norm. Okay, sometimes you put here a 2, I'll just put it in red if it's not clear from context that it's a Euclidean norm. Don't confuse a 2 here by putting a 2 here, which is squaring it, which undoes this square root. Okay, all right, so the Euclidean norm is going to be the sum of di squared, all that to the power half. Okay, so the power half means the square root, and summation notation, you'll see much more in the weeks to come, and you've seen it before, I'm sure, but you'll revise it in the weeks to come. So it's d1 squared, etc., etc. So yes, you can use other distance measures, but certainly basically in your algebra, it's the Euclidean norm. The L1 norm, which doesn't take here squaring, but just does absolute value, is very common in statistics and data science for multiple reasons. Okay. All right. So the way to look at a distance between two vectors is to look at their difference vectors, and we can subtract vectors because, you know, we can subtract matrices, we can subtract vectors, and then to look at the norm of the distance vectors. So you could see that, for example, you know, on the y, I gave this a bit of an angle here, but really it's 182 versus 183. It's really the coordinates of the y, but I mean, the vertical coordinates are there's not much contribution coming from this because this is just -1 squared, this thing, and this is, what is this, -20 or 25 squared. Okay, so the distance between these two vectors is the square root of 25 squared plus 1 squared, so it's approximately 5. Okay, it's a square root of 26, which is approximately 5, just over 5. Now there's a comment, when we say L1 norm or L2 norm, it basically refers to way in which we find the distance between the two parents. Yes. Yeah. So in general, if you want, just so you want to know, so when you have this vector d, okay, and you do the p norm, what you mean is sum I 1 to n di to the power p, and here you do 1 on p, absolute value. Okay, that's the p norm, but basically we use p1 and 2 in data science. Okay. If p goes to infinity, then what you're doing is a supermoon norm, and then so you put d infinity, and that's the max of I 1 to n of the absolute value of di. But that's kind of beyond what we need. Okay. So back to vectors and distances. So norms are very natural, very important. And we can also, by the way, speak. We'll do about it more next week. We could speak about norms in the context of inner product. So we could have written this as D transpose D. That's an inner product. Okay, inner product. So an inner product of a vector with itself is a norm squared. But I won't tire you with this because I want to do something with these norms. Okay, so we had this person X, I'm reminding you, that's me. Here I am, Yoni. And person Y, let's not disclose your name. You fit good BMI person, extra smiling with teeth, etc. That's person Y. And X is kind of close to Y because, you know, those two coordinates, these ones are close and these ones, well, okay, so you're a bit thinner and leaner. Fine. Okay. Now, I want to speak about a data science application that requires nothing but thinking of norms, nothing but thinking of norms. And that data science application is k-means clustering. Okay, it's well, clustering in general, and k-means is an algorithm for that. All right. So let me explain. Let me explain the use case. And this is a special case of unsupervised. I'm trying to add pages and they don't seem to be adding. There we go. Okay, let's just go here, and I think it's okay. This is a case of unsupervised learning. Okay, so unsupervised learning, and what we're going to look at clustering, and we're going to look at k-means, which is one form of clustering. Okay, that's k is going to be a parameter, but also the name of the algorithm. Okay, so again, we're in this course, Math7501, we're certainly not teaching these methods that, hey, go ahead and take the method and go with it and you're ready to use it. But we're actually showing you how the bit of mathematics that we've just touched with, vectors and matrices, in this case, we're stopping in norms, has to do with data science. And is it a stats concept as well? There's a question on the chat for sure. Yeah, I mean, the line between data science and stats is, you know, is quite fuzzy. Okay, so let's go back to this weight height example and put here weight and put height. And what I'm going to do is I'm going to put a bunch of individuals. Suppose we have individuals with weight and heights. Okay, and I see these individuals. Now, you might look at this graph and you'll say, ah, okay, I see what's happening, or this plot. You see there's this group and there's this group. Okay. As a human looking at data, you can just do this. You can just look at it. Okay. However, this is just because we have weight and height. What if we didn't have just two variables, weight and height? What if we had 20 variables? Age and income and all kinds of things. And what if we didn't even have 20 variables? What if we had 1,000? Okay, how could you still cluster this weight and height into these two groups? So now these points won't be laying in two-dimensional space and be laying maybe in three-dimensional space. You could still visualize, but in four-dimensional space we can already not visualize. So four-dimensional vectors you cannot visualize. Okay, and certainly not 5 or 100-dimensional vectors. So what we want is we want some method, we want some algorithm that would take this data, and it's called unsupervised because beforehand we were not told that these guys here are of one type and these guys here are of a different type. Unsupervised learning, just like when a baby comes and explores the world as a baby or a little puppy or maybe a little kitten if you've seen one or something like that, explore the world, they don't get feedback of exactly what things are, but they make all kinds of connections. So we want an algorithm that will be able to look at this data and actually tell us this is one group and this is another group. Okay. And I'll present one such algorithm and it's called k-means, and hopefully, let's see, we've got 35 minutes. We might be able to implement it or just see it running. Okay. All right. Is the goal clear? All right. Now, the way the way k-means works is we specify beforehand the number of groups. So in this case, I'm just going to look at the data and I'm just going to say k, the number of clusters, is 2, number of clusters. Okay, this is kind of what you'd call sometimes a hyperparameter. Okay, you can beyond that go and you could maybe do all kinds of analysis with the data and look at different numbers of clusters. Okay, and I specify k equals 2. Okay, in this case, since the data is 2 dimension, 2 is also d is a dimension as well. I don't want to use d because I use that for difference, but it's a dimension. Okay, in this case, but I could have had in 2-dimensional data, I could have had also another group here, for example. Let's actually have this other group here. So, and that cluster would be in green. And let's say we look at this data and we decide that actually k equals 3. Okay, so again, this is 2-dimensional data, but we decide that there are 3 clusters. So this is how the algorithm works. Let me show you. We'll do it first manually, and then we'll use a bit of Mathematica to see it work. Okay, the way the algorithm works is we say that for each cluster which we will have, there exists a center of mass. Okay, there exists a center of mass for the cluster. So, for example, if we knew that these points are in a cluster, what we could do is we could take all of the weights. So I'm taking all of the weight coordinates, I'm dropping them onto here. Okay, so that's all the weights. And then I'm doing an average of all these numbers. So let's say that comes here. Okay, so you know how to do an average. I sum up all the weights and I divide by the number of points. And similarly, I'll take all of the heights. So I take them here, all of the heights, okay, for each point. And I do the average, and then this is average. So then the point of the average, let's do this in this purple, that's going to be this average point, okay? So just like you can average numbers, you can also average vectors, okay? Just to see it, look, let's do the average. I was Mr. X here, blue, and Mr. Y. We can do the average. We can do X plus Y times a half. That's, let's call this A, the average, okay? So that's 110 plus 85 over 2, and 182 plus 183 over 2. Notice that what I'm doing here, I'm doing vector addition, which is just like matrix addition. I'm adding element-wise, and scalar multiplication, okay? So in this case, A would be, I don't know, what's 110 plus 85, 25, 25, what is it, 198.5, maybe I made a mistake, and 182.5. To correct me if I made a mistake. Okay. It's going to be the average point. So you can always average vectors, okay? You can always average vectors. So if I go here to assume if I knew these guys were in a cluster, I could average the vectors and I'd say, oh, okay, the average point is here. And let's call this the center, you know, the center. And if we want to impress our friends, because I mean, you did spend all day studying data science, let's not call it the center, let's call it the centroid. But that's just center. So some people call it center, some people call it centroids, okay? You want centroid, let's call it centroids. We're good. Okay, so that's a centroid. Now, similarly, you could have had a centroid for other groups. Okay, so what I'm saying is when you know points are in a group, you can compute the center. However, now I'm going to erase this. All right. We don't know that all these guys are in these guys here on the top right or on the right that where I'm erasing. Killed it all. We don't know that these guys are part of a group. Okay, we don't know that these guys are part of a group. So what we're going to do in the k-means algorithm is we're going to part of a group, part of a cluster, okay? We're going to change between clusters, centroids, clusters, centroids, clusters, centroids. So let me explain to you how it works, all right? So let's just draw the points again. Of course, a schematic of the points. Now, of course, I'm drawing the points quite synthetically. They're quite separated. Often, they won't be so separated. Okay, and again, often they'll be in high dimensional data. So what we do at first is, if we decided we're looking at k equals 3, we just throw some 3 random centroids, okay, in this algorithm. We throw some 3 random centroids. So let's say one goes here, one goes there, one goes here. There are different ways to do it. You can choose a random, as you can kind of look at the range of the data and you pick uniformly within the range, or, well, the range in each coordinate, or maybe you could have picked 3 random points. But let's say these are now the centroids. So this is iteration 1. Picked centroids. And we did it randomly. After we do this, we can now see, if this is a centroid, we could see for each point which we can, let's say it like this. Let's not centroid. Let's speak about, say, this point, which I'll highlight. Say this point. We can ask this point, which centroid does it need to be in? Does it need to be in this centroid? Does it need to be in this centroid? Does it need to be in this centroid? So this point, which I highlighted, which centroid is it sensible that it's in? The northeast, the western, or the southern centroid? This point. The nearest, the one closest to it, right? Which is this northeast. Okay, this point should also probably be in this one. This point, it will look at the distance to this centroid, to this centroid, to this centroid. It will choose this centroid. So basically what we're going to do is, for each point, we will calculate the distance between the point and the centroids. So when there's a question, randomly means random bit groupings. No, what we did is we just threw some 3 random centroids. Okay, so I'll erase this green. So we started with 3 random centroids. Okay, 3 random dots. Okay, and then after we do this, we're going to see each point. Well, let's see. So this one is going to belong to. Now let's associate them. So let's do it. Say with this green. This one will belong to this. This one will belong to this. This one will belong to this. This one to this. This one to this. Well, this one maybe. This one to this. But this point here maybe it's closer to this. Okay, let's just assume that this is slightly closer. And this to this, to this, to this, to this, to this, to this. Maybe let's just, to make it a bit more interesting, let's say this one to this one to this, and this to this. Okay. So, and let's say that this, and this one to this. Okay. So after we pick the random centroids, we're running on the points, and for each point, what are we computing here? We're computing the Euclidean distance. We're computing the norm of the difference vector between the point of each of the centers. So the way we did this is we computed for this point, for example, we looked at this distance, we looked at this distance, we looked at this third distance, and we said the third one is closest. So that's how we did the association. So after we did this, then our clusters become, say, these things. Okay, I'll draw the clusters. So this was one iteration. Of course, the initial centroids were completely random. This algorithm, by the way, is a heuristic. Heuristic means it's not something that's solving something optimally. It's just something that generally works. And to tell you the truth, a lot of the things that we use in data science are heuristics. There are algorithms that make a lot of sense, that sometimes rely on complicated mathematics, sometimes not. This one is not really complicated mathematics, okay? And they generally work, but they have their caveats. So this is not optimizing an objective perfectly. Okay, so this was iteration 1. We're not done though. What do you think we're going to do now in iteration 2? So now we've got some candidate clusters. Okay, k equals 3. We've got some candidate clusters. What are we going to do in iteration 2? Suggestions. 3 new center. Come on, centroids, not center. Okay, centroids of clusters, exactly. So now what we're going to do, look, I'm gonna press you. I'm going to cut and paste this. Going to cut this. I'm going to do now well, I thought I would impress you. I want to move it, but I want to, copy. And then I do here, paste. There it is again. Okay. So here now we're in iteration 2. Okay. In iteration 2, what we can do is we can delete this centroid. Oh, I didn't want to delete the points. I just wanted to delete this. Okay, that's good enough. We can delete the centroids. Okay, I'm deleting this red guy. Never mind. It's just hard to delete. Okay, let's leave that third centroid. And for each group, we now compute the centroids. For each cluster, we compute the centroids. Now, the centroid is really going to be kind of around here, right? And the centroid for this one's going to be around here. The centroid for this one might be around here. Okay, and then we repeat. We repeat. So after we've got the new centroids, now we're going to look who's closer to the centroids. So as we move, the centroids move. And this can work for a couple of iterations until we stop. How do we decide to stop? How do we decide to stop? Some ideas on how to stop. Any idea? Okay, so that's an idea. So when the centroid coordinates do not change, that's one way of stopping. Okay, if you have zillions of points, then maybe you'd need a stop when your loss, you can kind of compute a loss with this, does not stops going too low. So you have some stopping thresholds. But here you'll actually stop maybe when the centroids stop moving, right? So the algorithm will just get stuck and stop. Okay. Ready to see it in Mathematica? That's k-means. Before that, I actually want to show you a use of that on kind of high dimensional data, or at least not low dimensional data. This was just 2 dimensions. So this course, I'll share this in the chat. This is a link to a course that I taught in the month of January this year, a deep learning course. Okay, and you don't need to know anything from this course for what I'm speaking about, except I just want to show you an example. It'll be very quick. So there we go. All right. So in the world of machine learning, there's a very common data set called the MNIST data set. Has anybody heard of the MNIST training digit data set? Now you'll see it in your degree here if you haven't. But the MNIST data set, you can see my web browser I said, right? I hope you can. Yes. Okay. So the MNIST, I'll put it in the chat as well. MNIST training set. Okay. So this is a set of images, okay, and each image is 28 by 28 pixels, okay. 28 by 28 is 784. So each of these images, you can think of this image as a matrix, but you can also think of it as a vector, okay. So what you can do is you can let me see if I can draw on the screen here. You can vectorize the image. You see I'm going with a line here. I don't know if you could see this blue. I'd go like column by column. Let me change that to red. So I'll go column, and then another column. This is called column age, and then the third column, etc., up to the last column. And I'll string out this. It's like taking this matrix, string it out to a vector. So that matrix becomes a 784 dimensional vector. Okay. And there's 60,000 such images. So if you would treat this as a data set, you've got 60,000 times 784 pixels. Okay. Now, after running k-means on these images, okay, and not ignoring the labels are the actual meaning of the digits. After running k-means on these images, what we can do, and with k equals 10, we can look at the centroids. Okay. And what we see here are the images corresponding to 10 centroids. Okay, none of these images here is an actual digit image, but it's actually a point in a centroid, so a point in 784 dimensional space, after we put it back to be a matrix, and then we plot that image. So you see, this 8 is sitting between a bunch of other 8s, and this 0 probably between a bunch of other zeros. So the result of the clustering algorithm is not just saying which clusters exist, it's also saying what are the centroids. These are like typical images. Okay, I hope that's kind of clear. I mean, you'll see this much more in a full machine learning course, but what I want to show now is here you cannot plot the points because each point, each image is 784 dimensional. That's quite high dimension. Okay. All right. So let me open now a Mathematica notebook. I'll just see if I could share like that, which will implement k-means. I thought I'll do it all from scratch, but we won't, just because we won't have enough time for it. Oh, I see. I need to open it. One sec. And you'll have this notebook in the GitHub. Okay, so sec. All right. So here in what you can do in Mathematica notebooks, you don't have to do too much for this course, but you can collapse and expand sections. Okay, so I've made this notebook earlier, and what I'm going to do is I'll explain to you step by step what's happening, and we might, given the time permitted, we might modify a few steps. Okay, so what we're doing in this first section, this thing is called a section, is actually creating some mock data. Okay, creating mock data is a bit of a funny thing. It's certainly not what you're going to do when you're analyzing data, but it's sometimes good for algorithms just to kind of create your own data set, just to play around. So this first command here sets a fixed seed for reproducibility. So when you're working with random numbers, sometimes it's good to fix the random numbers, even though they're random, such that when you run this file again and again, you get the same random numbers. For example, if you want to run this on your computer and you want to get the same exact numbers, even though this uses a random command by setting the seed to random to something arbitrary, this could have been some arbitrary number, okay, 3523. That's the seed from which the pseudo-random sequence is going to generate random numbers. So everything will be reproducible afterwards. Ask me if that's not clear. Okay, and what we're going to do basically now is we're going to generate this data set, okay, of kind of a heterogeneous data set of 3 different groups. But for this, we need a bit of parameters. So look, what I'm going to do is I'm going to do this nested list of means, okay? So this is the first group, this is the second group, this is the third group, okay? And we assume here we have 2 features, okay, like weight and height, okay? So this is like assume 2 features, like weight. Okay, 2 features. The word feature is synonymous with variable. In the context of vector, it's synonymous with the coordinate of the vector, the first coordinate, the second coordinate, etc. This k equals 3 is number of clusters. Okay, that's what it is. And what we're going to get is we're going to get 150 points from the first cluster, 90 points from the second, 200 from the third. And for each point, what we're going to do is we're going to generate from a normal distribution. The normal distribution, you'll see it somewhat in this course as an application of integration and derivatives and things like that. You'll see it in Data 7001, but you've also seen it probably before. It's a bell curve, okay? So we're going to generate random numbers, so random from a normal distribution, with a mean m and a standard deviation s. The standard deviation is the width of the normal distribution, the distance to the inflection point, actually. Okay. So these are standard deviations. And this function make point, what it does is it creates a random, this is like the x coordinate, this is the first feature, and this is the second feature. Okay. Now, all these things in Mathematica are sitting here in one cell. So just to make it easier, what I'm going to do, I'm going to put the cursor here, and in the cell menu, I'm going to go to divide cell. Okay, so I did divide cell menu to break up the cell. Okay, so I can run this cell above, Shift Enter, ran it. There was no output, but it defined these functions. And then I can kind of do, look, I can do, for example, if I do make point on a mean of, say, 100 and 100 with a standard deviation of 10, it gives me a random point around the center, 100, 110. Look, if I do it again, oops, another one. Do it again, another one, another point, okay? So now what we're going to do is we're going to do a table of many make points. So we're going to do make points of the means for each group K, K going 1 to KK, with a given standard deviation. Now, I didn't show you this, but when you have you'll see this probably with Amina in the practical, when you have a vec, you know, which is like, or just a list, okay, 1, 2, 3, 4, -4, 12, etc. Okay, if I do vec, for example, at the 5th position, this is how, you know, in Mathematica is get the 5th index. So indexing starts at 1, not at, you see, so the 5th index, 0, 1, 2, 3, what? Sorry, 1, 2, 3, 4, 5. Okay, so the 5th index is -4. Right? So here I'm taking the means. I'm taking from the means list, the first mean, the second mean, the third mean. The point is that here, after I've run this points, if I look at points, PTS points, I get this thing that's, you know, I can scroll down quite a lot of points. This is, I've now created the mock data, okay? So these points is a list of 3 different groups, okay? So it's a nested list. So if I look at, let me delete this so it won't take too much room. So I'll just select this cell and delete it, okay? If I look at the length of points, there are just 3 elements. But if I, for example, look at the length of points 1 of the first thing in points, there are 150 points, okay? If I look at length of points 2, there are 90 points, as I asked for, etc. This thing is maps the length function to points. Okay, so that's, this thing is a map. So it applies length to each of the points. This is really not critical for what we do. Okay, let's get to the point, no pun intended. I don't get any more comments on the chat. Did I kill everybody? I'm speaking too fast. I suddenly picked up because this is like a demonstration. This is not accessible content, by the way. Anybody there? Good. We've got. Good. I've got a few. Yeah. Yep. Yep. Yeah. Good. Yes. Okay. We get a lot of. Yep. Okay. My middle daughter, she typically says, "Still alive, somebody?" That's good. I get a yeah. That's a Y-E. Yeah. Okay. Good. All right. So here's our points list plot, and it actually plots them according to their different clusters of, that's the natural clusters. But this is like, this is nature. We don't know this. We just created this data. Okay. This is, so you see, we know this is from one group, second group, third group. But now what I'm going to do is make it one big group. Okay. And if I'll now plot this, oh, look, now we can't see who is what, right? So we'll want our algorithm to cluster it for us, okay? Okay, so this was all prep, all right? I'm gonna minimize this. You see, I double click on this collection of cells, so creating mock data is minimized. And now we're in the k-means algorithm. Let's do it. All right, so we've got our data, right? I can do our data. It's a list of 440 such points. Each point is X and Y. So it's a list of lists. Okay, that's the data. So the length of the data is 440. And the dimension, if I take, like, for example, just the first entry of data, that's a dimension. So it's 2-dimensional data, obviously. Okay, so if I plot it again, here's a plot. Okay, if you don't want feature 1, feature 2, let's say weight and height. Okay. So these are maybe not humans. I don't know what they are. Okay. So now when we look at this, we want to assume 3 clusters, and you can play with this. If we'd have more time, we'd play with ourselves. And let's assume 3 clusters, so k equals 3, right? We could have taken this, we could have looked in this, we could have assumed 4 clusters, 5 clusters, 6 clusters. And again, in a more practical machine learning course, you learn about a method called cross-validation, and that method will allow you to maybe choose what's a good number of clusters. So let's start doing our algorithm, but we'll start doing it step by step. We won't just give the full function that does the algorithm. Remember, what is the first thing that the algorithm needs to do? What do we need to do? What's the first thing we need to do? I mean, we have this raw data. What are we going to do? Random centroids. Perfect. Decide number of clusters we did, random centroids. Okay, 3 random centroids. Okay, so let's take the minimum and the maximum. This is just the range of the data. Again, there's different ways to choose random centroids. You could have just picked random points and used them as centroids, okay? And so then we'll make this function RP. So every time I do RP, it's going to give me a random a random point. Okay, this kind of assumes that we live here in the same range of the 2 coordinates, but that's fine. By the way, often when you get data, you'll first standardize it. So it's also you'll put it all kind of, you'll do standardization. You learn this more in the intro to data science course if you haven't done that. Well, most of you have. Okay, so that's a random point. So here are 3 centroids. Here's the centroids, okay? So centroids this is the first centroid, second centroid, third centroid, okay? So let's here plot. This thing is going to plot the data and the centroids. And the plot style, it's going to put the data with point size, a small point size in black, and the centroids in red. Okay, so here we've got this centroid, this centroid, this centroid. Okay, these were 3 random centroids. Okay. Now, there's a question. I'm just wondering, do we have to make 3 center points? No. So in general, when you go to the data, you won't know the number 3. Here we plot it so we can see it. But again, it's easy to plot 2-dimensional data, how to plot higher. We chose k equals 3. If we'll have a bit of time, you'll go here and you run this again with k equals 4 or 5. Of course, the natural thing for this data is to have k equals 3 because we engineered it this way, right? We engineered the data to have k equals 3. Okay. Okay. And yeah, there's a statement, we use the elbow method, and yeah, you'll discuss this more in other courses, but k equals 3 is given here. Okay, so we've got the 3 centroids. At this point, finally, a bit of kind of linear algebra back to the rescue, or at least that's why we're doing linear algebra. We want to now calculate the distance from every point, like the one I'm pointing at, to the centroid. Every point to the centroid, every point to the centroid, every point to the centroid. Okay, so let's make this function here. This is a function called dist. Let's call it dist to centroids. Okay. Okay, dist to centroids. So it's going to take the ith point. It focuses on the ith point, and it's going to do the norm. So this norm, let's look in norm, Julia norm, not Julia, Mathematica norm. Okay, the norm is the norm of the number vector matrix. So if you look a bit more in help, you could go to that help, and you'll see that that's a norm just like we spoke about. Okay, so we're going to do the norm between the distance between the ith, well, the norm of the difference between the ith data point and the kth centroid. I is going to be a lot of things. I would be 1 to 440. K would be 1 to kk. There's a question, should you use this? Yes, because when you define a function, this is a typical way to define a function, this underscore. It's the function operating on a pattern, which works with I. Okay, if you would just do this, it would only work on the specific variable I. Okay, so what we have on dist to centroids is now it's going to do a table. What's going to be the length of this table in our, it's going to give us how many? 440 numbers or 3 numbers? 440 or 3? So say if I now do, I just did this and I'm going to do this to centroids on the 35th point. What am I going to get? 440 numbers or 3 numbers? When I now do shift enter. 440 or 3? You don't have much time. I'm going to guess. 440 or 3? 440 or 3. 3. Yep, it's these are the three distances. The three distances between the 35th point and the centroids. That's what it is. Okay, so now if we want the cluster of the point, well, now, okay, we're using a sorry, I keep saying Julia, mathematical function called ordering. Okay, so this basically, this is an ugly way to choose the closest index. Okay, so if you do this now, if you do current cluster on the, say, the 35th point again, it tells it 2. Why? Because you see 236 is smaller than this 36. If you would have chosen a different point, if you would have gone here to the 440th point, okay, so let's just update this 440, okay, then we see that it's going to be the cluster of 440. What's going to be the cluster of 440 of the point 440? 1. Perfect. Perfect. Okay. So now what we can do is we can apply this current cluster to all the clustering, and that's going to give us this cluster mapping. So look, if I look at this cluster mapping, this is actually our clustering. It says first point you're in cluster 3, second point you're in cluster 2, third point you're in cluster 3, first point in cluster 2, etc., 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 up to the last point. There seems to be some patterns here because we didn't shuffle the data. When we made the data, we didn't shuffle it, right? If we would have shuffled it, then you wouldn't have here all ones in the end and stuff like that. Okay, so then what we want to do here is this map point. This uses a pick function. So look for help of pick. Mathematica has too many functions, like a lot of functions. It's not one of these languages with a minimal set of functions. There's all these functions. So you need to know a bit what you're looking for. Again, you won't have to do a whole lot and you can gain help. This is not a mathematical programming course, but this is a demonstration using Mathematica. We really use Mathematica for its abilities to do analytic computations, okay? So the map points, these are the map points. And if we now do a list plot of the map points, so look, based on these three centroids, look, there was a centroid here. This centroid grabbed pretty much all these points, about these points. There was a centroid here. This centroid grabbed these points. Can you use MATLAB instead of Mathematica? No, because MATLAB doesn't have the same symbolic abilities. Okay, it has some, but it's not as much. If somebody really wants to make a case and not use Mathematica, then you know, we can kind of try to accommodate. But the few assignments, there will be a few things that are focused on Mathematica. Okay, so this is the second centroid, third centroid. Did we finish? No, we didn't finish. This was the first iteration. Okay. If you want to look, there's 3 map points. These are the clusters in the points. And now we are going to start iteration 2. Okay. So start second iteration. Now, in this iteration and onwards, we're not going to use random centroids. Okay. So what we're going to do is use mean for centroids. Okay. The centroids are the center of mass. So these are now the new centroids. So if you now want to look at the new centroids, you see these centroids, they're now the center of mass of these clusters we had before. And again, we can repeat the cluster mapping and pick the points close to these centroids and look what's happening now. Oh, that already looks pretty good, doesn't it? So in 2 iterations, this happened to kind of work. All right. Now, the true k-means algorithm will repeat this again and again. And if you want to see it done in a brute force manner, it's going to be done not with a stopping criteria, but with a for loop. And here it is. And what you see is, in this case, after 2 iterations, it already stopped and points have stopped shifting, or after 3 iterations. Okay. So if you look at the final ones, here it worked. Well, by worked, I mean we got some sort of clustering. Now, just in the minute before we finish, and you guys can maybe play with this yourself, but let me just do it for you here. Let's say we were to choose now 5 clusters. Okay. if we were to choose 5 clusters. So I'll just run everything again. Okay. So now we've got, oh, sorry. The problem is here with 5 centroids, I actually need to adjust this to 5 centroids. Okay, 5 centroids. So you see now we've got 5 centroids. Distance to the centroids is here. Clusters, okay, this was just some demonstrations, cluster mappings, map points. Okay, see, so now you've got 5 different colors, and it might not be the right fit. So if we actually go and let's just run it all here with 5 clusters, okay, something didn't work. Oh, because I needed again to initialize for 5 clusters. I don't know why I didn't. I think I'm missing something with it, something specific for 3 clusters, and I'm out of time. So now I broke it. Okay, I'll fix this and upload it, but to GitHub. But that's it. So are there any questions before we just wrap up? I'll steal another minute from your time on this very long day. Any? Again, these things like the k-means is just a demonstration. And the code which we use now is going to be on the GitHub repo sometime by midday tomorrow. Same with the lecture recording, by the way. You'll have a meeting with Amina this Friday and your scheduled tutorial time. You're free to jockey between tutorials or practicals, I should say. Okay, so the question, where will the lecture recording be located? On YouTube. So for this course, we just go to YouTube. And there'll be a link. There's a playlist here. So there'll be a link for the playlist. There's a YouTube playlist. Hi, I'm Yoni Nazareth. Oh yeah, so you've seen this, right? So there'll be the first lecture will be there. Okay, more things? Okay, please, those that haven't sent your introduction recording, please do. So just get to know you, because it's very just, the lecturer just speaks and, well, no, but I'm very much enjoying your comments on the chat and the few verbal ones. Okay, so, and what time is it now in China, just so we know, and time in India? I want to just, of course I could have done, but I forgot. So it's, okay, India is 15:22, 3:20, and China just 6. So enjoy, everybody, and see you next week then. And go to the practical this week. Bye-bye. Good night. Bye. Yeah, you can ask questions. There's just Yichan, go ahead and ask. I can stop the recording maybe or not. Do you want to ask a for everybody or for the few that are left?
Yeah, it doesn't really matter.
No.
Yeah, the questions that I want to ask is like for me, because I haven't touched math for like 4 years already. So in this case, for like a matrix calculation session, I still remember something, but like when the session you talk with use the mathematics to like demonstrate, I'm feeling a bit like misunderstand or thinking a bit delay. So in this case, do you have like any suggestion or videos or like any links about it to like help me to improve that?
Yeah. So in your case, go to this unit 1 here, And I would watch most of these videos. Okay, just watch. And in mathematics there's what's called active learning. You kind of watch and you have pen and paper and you compute in parallel, right? And you see in parallel that things work. Okay, so these are good videos that cover the bit of material. That's one thing. You can also join the first year mathematics learning center.
Okay. Do you think I need to find some like the question or exam paper to, or not exam paper, I mean the
Oh, yes. So
the
what you
repetition.
can do, yeah, so the way to do it, if you go to last year's course, so when you go here, I should have told everybody that, but you go to last year's course, for example,
Yeah,
and you would take like assignment 1, and you'd work on these questions in the first year learning center. So you kind of, and similarly with quiz 1 and the quiz 1
yeah,
solution, right?
yeah.
Um, you take these things for the learning center and they will help. And you can also go earlier. So the order might have changed a bit, but you'll see if you're doing the linear algebra, the matrix part, you're doing the matrix part. If you're doing the other part, you're doing the other part. Okay.
Okay, I see it
So
now.
yeah, you've got a lot of, since you've got links here for the course already 3 years back,
Yes.
you've got quite a lot of resources of assignments and quizzes that you could solve.
Okay, I see it now.
Yeah,
Thank
so
you so
there's
much.
plenty of stuff, right?
Yes, it is.
Okay, it's a time that will be the issue. Okay, yeah, but visit my visit hour as well if you'd like. That's tomorrow at 11.
Okay. Yeah, I will be joining that.
Okay, good stuff. Is that it?
Yeah, that's it. Thank you very much. Have a good
Yeah,
night.
you too. You too. Uh, two more people here. Would you anything else for anybody? Or no? Okay. So see you. Bye bye.